I'm going to go to the heavy nuclei. And the heavy nuclei, I got to compare two atoms now. So for the heavy nuclei, to really see what is going on, I have to take lead, right? I need lead. And we've already calculated the details of lead. And the other element I need is that I need bismuth, right? I need bismuth. And why do we need bismuth? Because it's the first unstable nuclei. So we really gotta pay attention to both of these. So one more time, this is the last stable nuclei or isotope. And that means it lives forever. This guy is the first radioactive, maybe let's not say radioactive since I haven't talked about radioactivity. This is the first unstable nuclei. So that means here it does not live forever. So if I start looking at the numbers, why is it that one proton and really one neutron or really changes this thing? So what's crazy about this is that bismuth, so, and I think this is what I mean by crazy. Actually, let's calculate the numbers and then I'll write the crazy piece. So if I look at lead, it's 207, 82. And if I look at those numbers, this is 125 neutrons. And this guy gives me 82 protons. So when I look at its ratio, look how interesting this number is. This number is 1.524. This is a lot of sig figs. But what does this tell me here? What this tells me here is that you get 52.4% more neutrons than protons. So what's the difference here? So when I look at lead, this is 209, 83, and then this is bismuth, of course. And so when I look at these numbers, this is 126, and this is 83 protons. So when I look at this ratio, is that the NP value then is 126 over 83, which then gives me 1.518. And look at the number, 51.8% more neutrons than protons. So what's crazy about this? You know, what I'm going to do is I'm not going to write crazy right here. I'm going to write it down below. And the reason why I want to do this is that I want to make some observations about this. Okay. Let's make some observations about what we just saw. So the first thing is that note that the difference between lead and bismuth is 1 neutron and 1 proton. Look at the numbers. If you look at lead, that's 82, right? So this guy tells us that this guy has 82 protons. This one has 83 protons. And the other thing here is that look at the neutrons. This has 125 neutrons. Let me move this a little bit more. And then this guy has 126 neutrons. So you could see that there's really one more neutron, one more proton in bismuth than lead. But lead lives forever, while bismuth does not. So just those little things, those one proton, one neutron, which doesn't seem like it's a lot, but it is. And then here's the thing here. For the first time for nuclides, NP ratio, the NP number, ratio number, drops from lead to bismuth. No other time in the periodic table do you see a drop in the number of neutrons and proton ratio. At no other time does this happen until bismuth. So that neutron-proton ratio becomes very, very important. And so what this is really telling us in this is that there is not enough neutron glue to keep the nucleus stable. Now, it's more complicated than this. It's more complicated than this. But if I keep moving along this direction, here's what we find that's really, really interesting. I think it's interesting, at least. Hopefully you will too. When one differentiates between a stable and an unstable nuclei, the water just gets murky. So when one differentiates between a stable versus an unstable nuclei, the waters can get murky or brackish. I think that's the way you spell murky. If it's not, it's okay. So what do I mean by stable versus unstable nuclei? And I think this is a really, really wild question. So what does it mean to be stable? So if we look at lead, for example, what we find here is that the lifetime of lead's most stable isotope, and there's 3 of them, 206. And remember, I told you that this is one of my favorite atoms on the periodic table. The history is just fantastic. So the lifetimes of lead's most stable isotopes, and here's the key thing, are too long to measure. And what that really means here is that because no one can make this measurement, lead is stable and lives forever. And here's where I say the waters get murky here. So if you focus on bismuth, it turns out one can measure the lifetime of bismuth. But it's super long. So what's super long? It's 10 to the 19 years. Okay, it's 10 to the 19 years. And this is just an astounding number. For example, so as an example, to give you a sense of what I'm talking about, the age of the universe, as far as we can tell, is 10 to the 14 years. So if you had a bismuth atom lasts longer than the age of the universe. So as far as I'm concerned, I would say, well, shoot, that is not unstable. That's longer, right? So this is 10 to the 5. So this implies here that bismuth lasts 100,000 times longer than the universe. And when I was a kid, that used to drive me nuts. I'm going like, you're kidding. How can you say that bismuth is unstable? It's 100,000 times longer than the age of the universe. But that's not the definition of something that lives forever. However, and this is the key point, because we can measure this lifetime, bismuth is unstable. Isn't that wild? I think that is so wild. That is always like going like, you're kidding me. And so when we start talking about unstable atoms that occur naturally on Earth, so then I'd probably say one last thing because I got to get the heck out of here. I got 2 minutes. Oh, I think I could make this. So for the unstable heavy nuclei that exists on Earth, we have 83 to 92. So let's go look at these things here. So if you look at these guys, again, it gets murky because this is 83, 84. And if I just keep going through these numbers, you'll see that there's a reason to all of this madness. So when I look at these unstable nuclei, what you're seeing here is that definitely this is our bismuth. This is our uranium. And what you find here is that of all of these, 2 of them you won't find here on Earth. And it's really a quantum mechanical reason why that is. And that's because nuclear physics is just more complicated. These 2 are not found in nature, but must be manufactured. What we find here is that we should talk about lead and bismuth. What's really the difference between them? So I start with the force picture. Now remember, everything that I have here has already been uploaded. And I mean, if you'd like to write it, it's going to be quite hard, but it's already on the website. So you should be able to just download it and look at it. So this is the new stuff. So I have a force picture and I have an energy picture. And the energy picture is the more important one, in my opinion. But it helps to have both so that you can get an overall view here. So here's my nuclei. And of course, there's a lot of protons in here, and there's no way I'm going to draw them all. But most of this is blue because of the neutrons. So you have a lot more neutrons than you have protons. So you should be seeing a lot more blue. So what am I seeing here? What I'm seeing here is that there's this very strong electrical force now. But now the strong force is just slightly larger, just slightly larger. So now we have these 2 competing forces. So I would say here is that there is almost a balance. But F strong edges out F electrical. It's just slightly bigger here. So the beauty of this is here, because now when I look at the binding energy is enormous at this point here, just enormous. And when you look at the electrical energy, well, it's really close here. And so when I compare these 2, what you're seeing here is that when I look at this, the binding energy is really containing the repulsive energy here. So the attractive binding energy is just large enough to contain the repulsive energy.